Hello, my name is Mike Cerrone, and today I will be explaining two different concepts. The first one is how to remove or reduce compilation dependencies, which is actually an item in Scott Meyers' book, Effective C++. And the other thing I will get into is move semantics, um, and get into move assignment operations, move construct operations, and how these move operations are more efficient and faster than their copy counterparts. So, the first thing that we'll get into is a look at how Scott Meyers' example, he uses a person class. I'm going to do the same thing. A look at how a normal class, which we all have come to get very fond of and familiar with, is is actually not too beneficial when it's used in a large project. The larger the project, the more detrimental it is that this structure is used. And the reason being is that anytime there's a change done to any of this, and anytime there's a change done to subcomponents that are a part of this class, like the address header here, um, the translation units that have person objects being instantiated, those translation units have to be recompiled. It's kind of a mouthful, but to say it again, anytime there's a change to any of this, then any client code that has person objects being instantiated, those have to be recompiled. Um, the reason being is because of how the stack works. So we're going to go over here. So if we have an example of client code, would be, let's say, the main function, and we have a local variable being instantiated, person p. Okay, so with person p, sorry, I had to clear my throat there. So with person p, um, when this local variable is going to be put onto the stack, and here's the stack. Normally we think of stacks as going from bottom to top, but the stack in terms of the computer is bottom or top to bottom. So the stack goes this way. When we add items to the stack, they get added to the bottom actually. Um, so we have person p, added to the stack, and let's say there's a few different parts of p. They're going to be different sizes. And because of the way the stack works and how it is able to access this data, it needs to know ahead of time when things are compiled what the size of P is, and resultantly what the size of all the other elements are. Now, how does it do that? It comes back to this class here. So the solution to stop or reduce the compilation dependencies is to get rid of any object definitions like here and here. Get rid of that from the client code that is calling person and resultantly needing to know the size of these object definitions. The way that the these object definitions are gotten rid of is one of two ways. The way I'm going to get into and describe now is via an interface class. So let's go ahead and look at the interface class now. With the interface class, we soak it in. Um, if you'll notice, we actually, or no, don't look at this yet. Sorry, look at this. This is the interface. Okay, so we don't have any object definitions like in the original person class. Now, you may think that they're there, but I'll explain it, and they're not. Um, we have references to our smaller classes, and references and pointers to classes are actually okay. They do not enforce a recompilation. So that's what we're doing here. Before we declare address, we're able to reference it, and we're not defining it here. So that means if we're not even changing the address here, because all it is forward declared. So basically, we were able to have this be what client code uses, and actually what this means is that anytime the implementation details change, which is in an implementation class, the client code translation units won't have to recompile. The only time that that client code will have to recompile is if any of the implementation or any of the interface here changes. So, if address becomes something like int or whatever, then there is a recompile that has to happen. So, to get further into it and show how it works, I mean, I've explained what it does as an end thing, but the way that it works is there is a person implementation class, person impl, and this extends the person base interface class, and it has the functions actually be implemented. Once again, any changes to these functions, the implementation of these functions does not result in a bunch of recompiling happening for client code that uses person objects, or rather person references or pointers to person. And the other part, of course, just to reinforce, as you can see here, address is being defined, and its definition, or there's an object definition of address in the class for person impl. Now, if the definition of address changes, which happens in address at h, then by way of how things are implemented here, as we've gotten used to, there won't be recompilation happening for client code across all the different translation units that use it. So, going on, we can see here that we have a factory function. To introduce it, since you guys haven't heard of it, presumably, this is the factory function for pumping out resource management objects that are have a template parameter type of person. I assume you guys know about how dynamic binding works, and what happens is client code it only has to make person references, and person references can be assigned to uh, person underlying person objects or underlying person impl objects. So in client code, which will only be of type resource of the type that references person, because we want to reduce compilation dependencies, it'll actually be pointing to an underlying object that is a person impl. And I can show you examples of that now by going to my client code example page. Before we go there, don't look at everything too quickly. Let me just point you in the right direction. So just look at this first line here. We have client code. We are making a resource management object that references a person. Now, behind the covers, this factory function person create returns a person impl object, but by way of dynamic binding, we are able to call all of the virtual functions that go with person, that are associated with our interface class. So, I think I've gone over everything I wanted to go over for reducing compilation dependencies. To maybe hit home with you guys the gravity of what this does, it's not going to be just one page where you're going to have client code using person references. It's going to be a lot of different pages and a lot of different translation units and stuff like that. So, by way of this framework that, first of all, very well, in a very good way, separates the interface from implementation. Sorry, it didn't make sense there. Okay, so the takeaways from doing this is that you have the interface and the implementation very well divided by using an interface class, which brings along its own kind of bag of goodies and benefits. And the second part is we're going to have a reduction of compilation dependencies. The only compilation dependencies we have with this setup is where the interface itself changes. So that's it for that first part. The second part I want to get into, which uses the interface class implementation, is move semantics. So move semantics is a recent C++ thing. It has it was incorporated into C++ back in 2011 as a part of C++ 11. The way that it works, actually, give me 1 second. I'm going to mute myself and take a drink of water. I'll be back in 1 second. Okay, so we're going to go to my whiteboard here, and give me 1 moment. Background there. All right, cool. So the best way that I can explain move semantics is by showing a string concatenation operation, or actually a chain of concatenation operations. So let's say we have a string S1 and its text is something like dogs bark. And we have another one, S2. It has some other text. I won't do it for being able to be more brief. String S3. Okay. Now we're going to make string S4 be equal to S1 plus S2, or plus empty space, plus another empty space, and before I explain this further, I just want to mention that this is straight out of a web article I found, which was really nice for explaining move semantics. Here it is right here. It is a Microsoft article, and I can link it later. This guy really does a great job of explaining it, and it was the most helpful page that I found for move semantics. So, the way that things were done prior to being able to move in C++ was like this. So we have our first operation happening, which is going to emit or output a temporary. We have S1 plus some space. This, if you don't know, this string literal becomes a temporary string object. Now, the way that things were done prior to move semantics was you would have a copy of S1 be made. So let's say copy. And you'd make a copy of S1. Then you'd have that copy be equal to itself plus the string object created from the string literal. Let's call that, I don't know, space string. Now, this operation here it is most likely, and at least from the research that I've seen, is that a lot of implementations will have a STL copy operation happen, which appends all of the values of or appends copies of all the values of the second string into this one. So the problem with this approach is for however many operations happen, the amount of work done is quadratic in its complexity. So, if you have a ton of these concatenations happening, the last one has to do a full copy of everything that all the units and characters that make up the strings before it has to do a full copy of that, and then do the append operation after that. That's very inefficient. So the way that things are allowed to happen with move semantics is anytime there's an identification of an R value, or rather an R value reference is what the term is, there is what I like to call a shallow steal of of data where there doesn't need to be a full copy of the underlying data. To explain that further, what what happens is, well, okay, so now we're in C++11 land. We are able to do move. This actually, this whole operation, it still does have to happen. Why is that? Is because S1 can't be tampered with. We know that S1 is an L value. We know that it's being observed uh, throughout the code for the lifetime that it has. And we can't do this append operation to it because that would be very unnice to code and client coders that rely upon this not being changed in an undesirable fashion, which would happen here if we did allow for a move operation to happen here. So this actually still happens the same, but for every operation afterward, we are allowed to do a move operation in the concatenation operation. So S1 or this whole thing here, this whole temporary object here, let's call that T1. It is now going to be added to, or it's going to be added with S2. So we want to do the temporary object T1 plus S2. So because of move semantics, and because of how T1 is a temporary, which is actually an R value reference, we are able to take T1's pointer, which points to the underlying actual data. I'm going to show it here as some bytes. So this represents all of the characters that make up the temporary. Because this is not being observed anywhere in the code and it's temporary, we can steal its pointer and make it a part of a new temporary that's made. So we still actually make a new temporary, but we have this new temporary steal the pointer of the old one, and so now this new temporary has the pointer for itself, and the old temporary, which is going to be going away pretty soon here because it's temporary, gets a null pointer. So it's no longer connected to the underlying data. So then the rest of the operation occurs, which is an add assign to the T2 here, the temporary, and that's an appending of the data. So what this means for the entire sequence of concatenations which occur here is that the performance is linear as opposed to quadratic, which is of course much more preferred. So that, I think, gets into explaining the benefits of move semantics and how they work, but there's some more rules that go into it, and to explain them, the best way to show it is this example. So let's say we have a function called foo, and we're going to make a string and give it a name, S1. So this is an L value inside of the function. So as we go through different operations within the function, it's an L value. But at the end of this function, we can actually return S1 we can return S1. So, it's going to return over here, whatever. Let's say there's a string return value here. We can return S1. The really nice thing is that this previously was L value is now treated as an R value and is a candidate for a move operation. That is because since S1 is guaranteed to be going out of scope because we are within a return operation here, S1 becomes in R value. So, outside of the function, if we want to, here's what would happen outside of the function. If we want to assign string s x is equal to foo, the L value that was an L value within the lifetime of the foo function is returned as an R value. So we have a move operation occur when that return value is assigned to sx. Just like we saw over here, the shallow data, the pointer to the underlying data for S1 is swapped and used by SX as its shallow data, and in place of the pointer that the S1 did have, it just gets a null pointer, and it silently doesn't delete anything because its shallow data is the null pointer. So moving on, let's go ahead and look at the client code here. Back with our interface class example, we see that we have unique pointer being used here. Unique pointer cannot be copied. It's a unique pointer. So that means that right here on this line, we're not having a copy operation happen. What we are having happen is a move construction. The factory function person create is returning a standard unique pointer of person. Now when this gets returned here, this person one gets the pointer data of the other unique pointer here. This one then gets a null pointer, so it silently destructs and destroys nothing. And unique pointer, the rule of how a unique pointer is the only thing that can own its underlying data is still followed, because there is in essence a transfer of ownership, and you only ever have one owning object at one time for the underlying data. And the last operation I would like for you to take a look at is the one right here. Yes. So here we have a unique pointer that is default constructed. And then we have a move assignment operation occur. We know it's not copy assignment because, once again, unique pointer doesn't allow copies. So it is a move assignment. We were doing the same move operation where the new owning object person 4, which is a unique pointer, gets the shallow data of the unique pointer created by the person create factory function. That latter unique pointer gets a null pointer and it silently destructs. There is one more thing I want to mention. That is okay. So here we see how we can use the standard move function to be able to, I don't know, what's the right word, to be able to flag its argument as a candidate for a move operation. So normally we wouldn't be able to have person 4 be a copy of person 1. Of course, once again, because person 4 and person 1 are both unique pointers and they can't be copied. But because of this standard move call here, we are able to have a move of the data that belongs to person 1 move over to person 4. So we're seeing some of the maneuvers that we can do with move. We could do move construction, which is this one. We can do move assignment, which is this one, and we can also do a standard move function, which takes an L value, which in this case is person 1, and makes it into a R value candidate, and allows for a move operation to occur. So that's it, and thank you for watching.